today we are going to look at characteristics of exponential functions. Like we did with quadratic, we looked at their special points, right? We looked at their key points. We looked at how does it grow, what kind of seams it have. We're going to look at the special, the exponential relationship. So before we start that, I'm going to ask you, so I told you that you need a paper with you, okay? And look at the piece of paper right now that you have in front of you, and tell me, for that piece of paper, how many folds do you have? How many layers do you have? So that piece of paper, how many layers do you have? One. Okay? I haven't folded it yet, right? Haven't folded it, I have one layer. Now I want you to fold that piece of paper in half. So fold it one time in half. How many layers do you have now? You have 2 layers. Right? So after this, right, you folded it once, you have 2 layers. Fold it one more time in half. How many layers can you count right now? 4. Fold it one more time in half. How many layers do you have now? 8. One more time. 16. All right. Why? What's happening here to your number of layers?
It's doubling.
They're doubling, right? So every time you fold it, the number double, because when you had 8 and 8, right? You had 8, but when you fold it, this part had 8, this part had 8, so that makes it 16, right? So you're doubling. You're multiplying by 2. That's what doubling means. Okay? Now after 16, what's the number?
Oh, 32.
32. And then 64, then 128, 256, right? So what I'm doing is I'm multiplying by 2. Now it's going to get to a point that you can't fold anymore, right? But you should know by now that it's looking like it's doubling and you know what's happening. Then it's going to be 512 and 1024. Okay? If you're looking at your numbers, you know they're doubling. What can you tell me about the numbers at the beginning versus my numbers at the end? What do you notice about the numbers at the beginning? And then what do you notice about the numbers at the end?
They're even numbers?
They are all even numbers because I'm multiplying by 2. But do you notice any difference in the change between the beginning and the end? The gap gets bigger and bigger, right? So you're starting with like small increase, right? Yes, it's doubling, but it's doubling, but because my number is 2, doubling is 4. So the only difference is just 2, right? But then at the end, you jumped from 500 to 1,000, right? So you see that's a huge increase, okay? Now, let's do our first difference. Do you remember what's the first difference? What do I do to do the first difference?
4 minus 2.
So you do y2 minus y1, so that's 4 minus 2. Remember that when I'm doing first difference, I am going from the bottom to the top, and I'm subtracting. 4 minus 2, that gives me 2. And then 8 minus 4 gives me 4. 16 minus 8. 32 minus 16. 64 minus 32. 128 minus 64. 256 minus 128. 512 minus 256. And 1024 minus 512. I can't do the last one, right? Because I don't have a number under. Is my first difference is constant? No. So I have to go to the second difference, correct? Right, because my first difference is not constant. What if the first difference is constant, that means what do I have? What kind of function do I have? Linear. Okay? So I have to move on to my second difference. So let's do the second difference. So I'm going to do 4 take away 2. 8 take away 4. 16 take away 8. 32 take away 16. 64 take away 32. And 128 take away 64. 256 take away 128. And then 512 take away 256. Is my second difference constant?
No, it's not.
My second difference is not constant. That means it's not quadratic. Have you noticed anything yet?
That the differences are the exact same. And
The differences are the exact same as your y value. Right? So if you look at your first difference, 2, 4, 8, 16, 32, 64, 128, 65, 12, these are the same answers that I got for the y value. If I do the second difference, I'm repeating exactly the same thing. Right? So, why is that? What if I do the third difference? Is it going to give me the same answers?
no, it's going to be the exact same.
It's going to be the same thing. Even if I do the fourth difference, it's going to be, so the difference is not going to work for me. That's basically it, right? If I keep doing the differences, that's not going to work for me. So I know this is not anything that's linear, quadratic, cubic, nothing like that, okay? So here's where I have to test my first ratio. What does the word ratio mean?
Ratio?
Yeah. Hmm?
I said portions.
Which means what? Portion, right? That's what you're saying. Which means what do I need to do to find my portion, to find my ratio? Do you add, do you subtract, do you multiply, do you divide? You divide. You divide. Ratio means you're dividing. Okay? So same as your first difference and your second difference, you're going to do a division. Okay? Let's see if I divide, what am I going to get? So always, when you're doing your first ratio, you're going to have the y values, okay, to your original y values. And then we're going to do the ratio. So the ratio is y2 divided by y1. So when I'm doing the ratio, I'm doing y2 divided by y1. Remember with the difference, we did y2 minus y1. But with the ratio, we're going to divide. Okay? So what's 4 divided by 2? 8 divided by 4. 16 divided by 8. And then 32 divided by 6. So everything I do here, it's going to give me 2. Was this a surprise for you that your answer is 2?
No. It's times by 2, so it's divided by 2.
Because we're saying that it's doubling, right? We said already that our layers are doubling, right? Since they're doubling, that means my ratio is 2. Okay, so far, what I know is that the number of layers is increasing, is doubling. And I know that if I do my first ratio is constant. Okay? Now let's look at graphing it. So if graphing this, that's not, obviously that's not going to be, I'm not going to be able to fit all my numbers, right? Because I'm going to get to 1,024, right? But what I can do is, let's say if I go up by 100, okay? So instead of going up by 10 or 2 or 4, if I go up by 100, that's going to be tough. But let's try it. 100, 200, 300, 400, 5, 6, 7, 8, 9, and 1,000. And I have 1 fold, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is the number of folds. Anytime you are graphing, you need to graph you need to label your X and Y. Okay, number of layers. So if I have 1 fold, what was my So I had 2 layers with 1 fold, right? So it's somewhere like very, very close to this line, because remember this is 100, right? 2 fold I had what? 4. Again, this is going to be very, very close. 3 folds. Again, it's not going to change much because this whole square is 100. Okay? 4.
4 is 8.
No, 4 was not 8. 64. 16. 32. And then 64. 64 is right above the middle, right? Because half of it is 50, right? Then 7 is going to be 128. So that's somewhere in a second. At 8, what was it? 200, what was it, 8? 8 is 256. So if I'm looking here, that's 200, that's 250. So here, for 9, what was it for 9? 500 and something. And then 10, it was 1,024. So for 10, I'm going to be somewhere above here, right? So you see right here, if I'm going to graph this, it's going to look some kind of flat, and then it's going to increase, and then increase, and increase. So you see that my first 7 points were within the first box. Okay? What do we call this kind of graph? Does it look quadratic to you? No. Does it look linear to you? No. What does it look like? Is it growing? And then which way is it growing? So it's a exponential growth. We call that exponential growth. Okay, so we see that at the beginning it's growing slowly, and then we get to a point that our numbers are going too fast. Okay, our next point is going to be in the 2000s, and then the next point is going to be at 4,000 something. Okay, so you see that the numbers are growing fast. At the beginning it was slow, then we have exponential growth. So if I'm going to describe this, I will describe it as flat on one side and an exponential increase or a fast increase on the other side. This is how I would describe it. So I see like flat on one side and a fast increase, right? Or followed by a fast increase. Any questions about this? Now, if I'm looking at this, why did I do this on the other side? Even though it's a negative, so on this side you have the negative folds, okay? What does it mean by negative folds? What am I doing? Instead of folding, what am I doing to the piece of paper? So it's already like one piece of paper. Where is the paper? Give me a piece of paper, please. Okay? So the piece of paper is unfolded. Okay? How would I determine, so this is when I have 0 folds. I haven't folded it yet. Okay? If I'm looking at the negative, what would you think the negative would be in this scenario?
To take away some of the paper.
That's right, to rip it in half, right? To rip that paper in half, how many layers do I have?
Essentially perfect.
How many layers do I have?
One.
Half of it, right? This is the full layer. This is half of the layer, right? So if I have half a layer, now what if I break that half in half? I have quarter of the, yeah, 1/4, quarter of the layer, right? What if I rip it in half again? 1/8 of the layer, right? Now these numbers are very close to 0. If you put 1/8 on the calculator, that's a number that's very close to 0, right? I'm still very close to 0. Still haven't gotten to 0 yet. What if I rip it in half one more time? 1/16. Do 1/16 on the calculator. What do you get? In decimal. 0.0625. I'm still close to 0. I'm not at 0 yet. One more. That's not in half anymore. 1/32, right? Then 1/64. Then 1/, whatever the number is, 112, 150, whatever, right? Even if I can keep ripping this apart, even though I can't physically anymore, like can't physically anymore fold it in half, right? But I can technically still ripping it, and I can go microscopically and look at it as a cell, as microscope, okay? It will never, ever, ever, ever turn to 0. Because even if I keep ripping it apart, I can even go deep into the molecule and look at the inside of it, okay? It will never disappear. It will be hard to see, it will never disappear, okay? So that's why you see it flattening out right here, because that's flattening out close to the 0 line. It's going to flat out close to the 0 line, but it's never going to touch it. So this is going to keep going this way, and it's going to be as flat to the 0 line as possible, but it will never touch that line. Does that make sense to you? Okay. So let's see. We've already talked about this. We've already mentioned all of this, but let's write it down. Describe how the number of layers changes as the number of folds increase. What did we say happened to the number of layers? It doubles.
Put a therefore statement.
It doubles each time. Which means it grows exponentially fast. Now it's asking us to calculate the first and second difference in the table, and what do you notice? We already did the first and second difference. What did we notice about the first and second difference? Are they constant?
No.
So the first and second difference are not constant, but what did we notice about the numbers?
They're all the same.
They're the same as the y values, right? So they grow just like the y values do, right? So, do you notice a pattern in the table? Describe it. Can you create an equation to represent the relation? So what's happening to the x values? If I go back to the table, what's going on with the x values? What's happening to the number of folds? Increasing by what? 1. What's happening to the y values?
Increases by 2.
They're not increasing by 2, they're doubling, right? So they're multiplied by 2, right? Okay. So the x values are increasing by 1, so that means you're adding 1, right? So the x values pattern goes up by 1. The y values are multiplied by 2. Each time. So how can you write an equation for this? So if you fold it once, what do you have? How many layers? 2. If you fold it twice, how many layers do you have? 4, because you're multiplying that 2 by another 2, right? If you're folding it 3 times, how many layers do you have?
8.
Because you're multiplying 2 by 2 by another 2. Right? If you're folding it 4 times, what do you do? 2 times 2 times 2 times 2. You guys see what's going on here? What's 2 times 2? How can I write that as a simplified format? 2 squared. How about 2 times 2 times 2 times 3 times? 2 to the power of 3. How about this one? How about if I have 5 folds? How about if I have 6 folds? 2 to the power of 6. So if I have n folds or x folds, so what would it be? 2 to the power of x. So my equation is 2 to the power of x. My equation is y equal 2 to the power of x. Because, right, when I fold it once, it's 2 to the power of 1, right? When I fold it twice, it's 2 to the power of 2. When I fold it 3 times, it's 2 to the power of 3, because it's a multiple of 2. I am multiplying by 2 each time, I should say. Where do you think that 2 is coming from? Do you think that has anything to do with this? Yeah. Right? Because I am multiplying by 2, right? Because you're doubling, right? That means your base is going to be the same as your ratio. Right? So if you're tripling, what would be your base?
3,
3.
4, and
Depends on what you're doing to your numbers, right? So that ratio is always going to match the base. Okay? What am I starting with? How many layers am I starting with? One layer, right? So if you see here, if you look at this one, right, I can do my a value here is 1, right? It's 1 times 2 to the power of x. But I don't write that one usually, right? I don't write it because 1 multiplied by anything is whatever that thing is, right? So that's why I don't write it. But the minute, let's say if I started with, instead of starting with 1, I started with 10, then my initial value is going to be 10. So my a value is going to be 10, right? Because think about it this way. Let's say you have a bacteria count. You have 10 bacteria and they're doubling every single day, right? You have 10 bacteria doubling. 10 double for the next day. How many do you have? Then you have 8, right? So your first day 0, you have 10. So that's your initial count, right? So because that's my initial count, that will be right here. We're going to talk more about this as we go. But for now, my initial count is 1 layer.
The initial counters are each other?
That's right. So we'll talk more about it as we go. Okay? So, we did calculate the common ratio, right? And we said to find the common ratio, you do y2 divided by y1. And what did we notice about the first ratio? We said that the first ratio are constant. And that's what makes me know what gets, this is because the first ratio is constant, then I know it's exponential. Okay? For me to define an equation as exponential equation, how do you know that something is quadratic? Let me see what's on the next page. So this way. Okay. That's going to take me to it because I was going to X without. So let's do a quick review of what we've learned before and how does that compare to what I'm learning now. Okay? So for a linear equation, what's the degree? What's the degree of my my equation?
1.
Degree 1, right? So I have an equation that would look like y equals something x plus b, right? Where my degree is 1. Right? And then for my table of value, what would be constant? First, difference is constant. And how about the graph? How would the graph look like? Straight line. So it's a straight line. Right? And then it's going to look like, doesn't matter as long as it's a straight line. Right? How about the quadratic relation? How would the equation look like? Has a degree 2, yeah. And then the equation is going to look like y equals ax squared plus bx plus c, right? Where you have a degree 2. And then in table of value, what would be constant? Second difference is constant. And then what would be the shape of the graph? Parabola. And then it's going to look like this or this, right? It doesn't matter, either opening upward or opening down. For an exponential relationship, your equation is going to look like this. Y equal a b to the power of x. So in this case, a is your initial value, so we're going to talk more about this later. So a is your initial, b is your base, or that's what your ratio is. X is your exponent. So your exponent is the one that's going to be unknown, is your variable. Okay? So the exponent in the exponential format is the variable. This is how you're going to know that it's exponential. Okay? So an example would be if I have y equal 10, 3 to the power of x. Okay? So 10 represents my initial value. B is my base, which is 3. And then what's my exponent? X, which is the variable. Okay? So if your exponent is a variable, which you don't know what it is, it's a variable, then you know it's exponential. Does that make sense? In the table of value, what would be the constant?
The first ratio.
The ratio, yeah. So to find the ratio, what do I have to do?
Divide the y.
Y2 divided by
Y.
y. And then your graph is going to look like,
Around.
so two different graphs you might have. So it's going to look like flat on one side and then increasing on the other side. Or it could be decreasing and then flat on the other side, okay? So it could be increasing or decreasing, right? As long as it's flat on one side and then on one end and increasing / decreasing fast. So it's either increasing or decreasing on the other.
Is there a name for that?
We will call it, this is how you're going to describe it, but it's going to be either exponential growth or exponential decay. But when you're describing your function, you're going to say it's flat on one end and increasing or decreasing, depending on the graph, on the other. Let's look at some examples. So if you're looking, examine each equation, determine the type of relationship of relation, it represents linear, quadratic, or exponential. So if you look at the first one, what can you tell me about the first example?
Exponential.
Exponential because?
Exponent variable.
Yeah, that's right. The exponent is a variable. And that's why when I say, guys, when you're writing something, eyes on me please for a second. Let's say if you're writing this and you're writing it like this for me, right? Is this the same thing as this? No. So when you're writing it as an exponent, I want to actually see something as an exponent, okay? When you're writing x squared, you have to write the 2 as a smaller number on the top, right? If you write this, that doesn't mean x squared to me, right? So please be careful when you're writing and how you're writing it, because it makes a big difference, right? So exponential, and then the reason for that is the exponent is a variable. Oh, come on. How about the second one? And how do you know that?
Because of the square root, yeah.
Degree
Degrees
2. Linear
Degrees.
degree 1. Are we okay with this? Complete each table, determine whether the relationship is exponential, give a reason for your answer. So the x value is -2, and my equation is 3 to the power of x. So I'm looking for 3 to the power of -2. What is 3 to the power of -2?
3 times -2.
No. Is it -9?
Oh, 8 times. Oh.
It's 3 times 3.
Oh, is it 1.5?
It's negative. But
What does it mean when I have a negative exponent?
Oh, 1
Or something
over
in that
3 to the power of 2.
Yes. Which is equal to?
1 over 9.
You guys killed me there. What's 3 to the power of -1? One over 3. You guys don't want to talk anymore. 3 to the power of 0? Good. 3 to the power of 1? 3 to the power of 2? 9. Do you know if this is exponential or not?
Yes.
How do you know?
Because of the exponent.
Yeah, because if you look at the equation, right, your equation is 3 to the power of x, so your variable is an exponent. So we already know this is exponential. This is not, unless I give you this, right? If I give you this, then technically it's going to be, you're going to have to find out, right? Now, if you want to find out your first ratio, what do you have to do? Divide what by what? Don't say just divide.
Negative 1 by negative
Oh my gosh, no.
What do you divide?
The
The
y
y.
value
The y value. So the first one you're going to divide 1 over 3
divided by 1 over 9.
divided by 1 over 9. So do that. 1 over 3,
How do you do that though?
you have calculators. 1 over 3 divided by 1 over 9.
The 3.
Put 1 over 3 in bracket. So do this. You can do this. Look.
1 over 3.
No. 1 over 3. So you can do this. Wait.
Can't you just do 1 divided?
1 divided by 3 in bracket divided by 9. So you can do that on the calculator. If you have a good calculator that has a fraction button, you can do this. Oops. This should be a square. Right? Where you have 1, 3, 1, 9. If you have a good calculator.
Oh, wait.
It's 3.
It's 3. Right? So when I divided 1 over 3 by 1 over 9, I get 3. How about if I divide 1 divided by 1 over 3? 3 divided by 1. 9 divided by 3? Guess what? Did you expect that? Yes, because my base is 3. My base is 3.
Why is math funny?
All right. Do you think that's exponential?
Yes.
Why do you think that's exponential?
First ratio is constant.
So here's what I'm going to do. I'm going to skip the next one. I'm going to let you have fun with it later after I finish the lesson. Okay? We're going to look at that later. So you're going to have fun with this later because I know you like math and math is fun and all of this. So you're going to have fun with this later and then we'll take it up. You might not be able to see this. You might not be able to see this on your thing, so you probably want to.
Oh, yes, I can.
You can? Okay. All right, so maybe you want to add it in. It's been 40 minutes. Let's go. Let's finish this. What kind of graph, what kind of relation do I have, or what kind of function do I have for the first one? Quadratic, and how do you know that?
It's a parabola.
Good. And then for the second one, exponential, and how do you know that?
Flat on one side, it goes up really, really fast.
That's right. So flat on one end, and then grows fast on the other end.
There has to be a faster way to write.
Round.